thank you for joining this developer session. So, as Yash mentioned, I will talk about debugging tools and correcting tools available on Aurora. Uh, to save traffic, let me turn off my video. Okay, so this is agenda for today. So for the debugging tool side on Aurora, I will talk about some preliminary steps for debugging on Aurora system, and then I will talk about Intel GDB OneAPI and then Linaro DDT as a parallel debugger at scale. And then I'm going to talk about the correcting tool called Intel Sanitizer. So I can detect several the issues, for example, some out of bound issue, data race, data deadlock, and some initialization errors, something like that, right? So this is quick agenda, and also if you have any question during my talk, you can also put your question on this chat, or you may just unmute and speak up your question. We can talk about it. So I just want to make more interactive session. Okay. So, in order to use debugger on Aurora system, for example, GDB1 API or DDT debugger, you need to compile and link your application with -g. This is required. So otherwise, you cannot see any source line from your debugger. It's very hard to find out what's wrong in your code, right? So -g is required. But just with -g, sometimes your local variable interest could be optimized out, right? So for the best practice, we recommend to build and compile and link your application again with -g and -o0 for debugging. So that is best to understand what's wrong, what's going on in your kernel, and then how you can fix the bug, right? And another step required is before debugging your application with GDB1 API and DDT on Aurora compute node, you have to explicitly enable GPU debugging configuration on all GPU you are using. So we want to minimize any performance interruption by the debugging configuration. So by the default, we disable this GPU debugging mode. So in order to debug your code, you have to enable that. A way to do that is you can create a script and execute it across all your compute node using MPI launcher and MPI XCC. So on the next slide, we have an example script called helper toggle EU debug.sh shell script. And then this script will take argument 1 to enable your debugging, and for 0 to disable it. So once you have interactive jump mode or maybe on a batch mode, right? So you can issue the following before starting debugging. So first of all, you may need to check how many nodes you're using, right? So you can manually type it, but you can also use a PBS node file to grab number of nodes. Using the wc-l and PBS node file, you can grab the how many nodes you are using. And then using MPI launcher, you can run this script, helper toggle EU debugs shell script, and then put the 1 as parameter argument, right? So once you do that, all the GPUs are debugging mode is enabled, and then you need to put this additional environment variable for debugging. GET enable program debugging is equal to 1. So once you do these two steps, your compute nodes are ready for debugging. So this is required for GDB1 API and DBT. Okay, and next page, you can see the helper toggle EU debug.sh shell script. So you can just simply copy and paste on your terminal. And also, we have the ALCF user guide link. So I will share it at the end. And if you go that user guide, you can also grab this shell script. So you can use it for debugging mode. So Intel GDB1 API. GDB1 API tool is a part of Intel OneAPI software, and it is available through the default module loaded on Aurora. So whenever you start some job or even on the login node, you see the OneAPI module is loaded by the default, right? And GDB1 API is part of that, so you don't need to worry about loading additional module to enable GDB1 API. You can just use that. This GDB1 API provide all the standard GDB features and it support for C, C++, SQL, Fortran code, and OpenAPI code for both C, C++, Fortran. And you can debug host side, kernel side together in the same session. And you can automatically create, it will automatically create inferior to debug GPUs. And it also display lane information and switch among the lanes. So at the bottom, you can see fundamental GDB command. You can use that, right? So help is the most helpful comment. So you can just help and comment. You can see what kind of option you can use. Run to start your program on the debugger side, and then you can also put some argument. Break file and line number. You can define the breakpoint on specific line of a file. And you can also check how many, you can also see the defined breakpoint using info break. You may delete using delete breakpoint using the delete. And step and next, you can just move forward line by line or the step into or over the function call. Or you may want to see the argument of local variable of a current function. So for that, you can use info arg or info local. And if you are interested in the specific value of the expression or variable, you can just print and the variable, and then you can see what's going on over there. And you may want to examine the memory at the specific address. In that case, you can just use x/format and address. And you may go up and down in the function stack, call stack. And if you want to disassemble current function, you can just disassemble on GDB line, and then backtrace will give you the function call stacks. So this is most basic one, and probably you're more familiar with more commands. You can use all the GDB standard command here. So GDB uses okay. Do these same instruction apply to Polaris? Our hardware watch expected to work on GPU? Yes, you can. GDB one API is not available in Polaris, but we also have another GDB from the NVIDIA side, right? So you can use that and the same instruction, and then hardware watch point expected working on GPUs. Yes. GDB uses inferior object to represent state of the program execution. Uh, so GDB debugger create the inferiors that attach to GDB GPUs to receive event and control GPUs. So on this slide, you can see once you start the GDB1 API, it creates two two inferior connections. So inferior one is Linux native target. This is to debug the CPU part. And then it also creates the inferior 2 for the remote target. In this example, we use it to debug a GPU. So this is very simple example. You can build your application with --0 and then start your application with GDB, right? And then you set the breakpoint and run. And if you check info inferior, you can see the two connections. One native connection shows the process. Then the second connection is device one using GDB server-GT, and then the process ID with from the native, right? So this is kind of the basic structure. And if you have multiple GPUs on the same node, even though you don't use all the GPUs, but the GDB attached to all the available devices, and then if you do the info inferiors, you can see multiple devices on the connection too. So multiple lines of connection. That is happen on the Aurora node. This is a GDB command relevant for GDB GPU debugging. So info inferior, you can display information about inferior. And GPU debugging will display additional inferiors so through the GDB server. And input thread, you can display information about thread and then active SIMD lane and thread. Command, you can switch context on the SIMD lane or thread, right? And thread apply with the command line, you can apply command to the specific lane of the thread. And set schedule locking on step off. This is important because even on the single process, your your GPU run the multiple GPU thread, right? So if you set breakpoint, then you may expect, if you step, you may expect to move on. That thread is moving on to the next step, but it doesn't happen because it has multiple the GPU thread is going on. So maybe instead of step forward, you may just see another GPU thread is just kicking in and then hit the breakpoint, and then you don't see any moving forward, right? So for that aspect, you may just lock your thread scheduler. So using the set scheduler locking step, that means you just keep other threads stopped while current thread is stepping. Or if you just set on, you may just resume and then while the other thread stops, right? So in that case, you can avoid interference. So by the default, it's off. So we recommend to use on or step if you want to looking into specific GPU thread. And you can also set non-stop on and off. So by the default, it's off, which means when you thread stops, or other thread stops, right? But if you wanna, for some reason, if you wanna let other thread keep running, you can also set the non-stop on. And print T mask, you can inspect the execution mask to show the active lane. So at the end of this slide, you can find several links for the Intel GDB documentations. You can find more informations. And also we have nice GDB deep dive talk presented by that engineer this May. So we have that link as well on the ALCF site, so you can also check it. So how to run the application with GDB OneAPI? So in order to start debugging on a single GPU, it's very simple. You can just put the GDB1 API -q, and then you're just run the application, right? On debugging, you may also use GDB1 API with the multiple API ranks or some API application, and you may just attach GDB1 API or one of the API rank. So for that, you need to use xtom because as you can see in the previous example here, once you start GDB shows the debugging information for specific the rank, right? So to use GDB on the API example, you need to enable the X11. So for that, you need to X11 forwarding set established from your local system to Aurora login node. So you need to SSH-y and to the aurora.lsf.gov, right? And then once you start, and then when you start your compute node, you also need to establish X11 forwarding using qsub-x and then the compute node. So once you establish that, using the npmd mode, you can attach GDB using the xtom. So in this example, I'm running my application with 12 MPI rank using npmd mode. So first MPI rank running without GDB. Second MPI rank using xtom, I attach GDB1 API. Then remaining the 10 MPI rank, I just run the application without the GDB1 API. So once I run it, what happens is through the X11 forwarding, Xterm will show up, right? Like this one, and then you can just set the breakpoint and then run, and then maybe set schedule locking, and then step and checking, etc. Right? So if you attach two GD1 API using the npmd mode, you may see two different X11 popping up, and then you can control that, right? But honestly, this is not really user-friendly environment for debugging MPI applications, right? So for that reason, we want to use a little bit better, a little bit user-friendly the better debugger, and we support the Linaro DDT. Linaro DDT is widely used for debugging parallel MPI and threaded application HPC system. And its graphical user interface provides a simplifying, easy-to-use method of debugging application at scale on Aurora. So in many systems, people can use 10% of system or 20% system with DDT. So it's pretty scalable and user interface is very intuitive. For the best practice, we recommend you to download and install the Linaro Forge client 24.1. The reason I'm specifying this specific version is the current default Forge module version is 24.1.2 version. So in order to use that, you have to have the corresponding client version. So 24.1 will work. We are working on the USDK you are working on the USDK on Aurora. So once we have that USDK, we plan to deploy the Linaro Forge client, Linaro Forge 25.0 version as well. So once we have that, you may need to update your Linaro client from 24.1 to 25.0 version. So if you click this link, you can go to uh, this site, Linaro site here. So right now, the 24.0.4 version is the default version. So you can, but on our system, we are using 24.1 version. You need to download the corresponding version. So go to older version and you can see the Linaro 24.1 version. So on my system, I'm using Mac. I downloaded this one. But depending on your operating system, you can download some corresponding version on your system and install that, right? So,
JaeHyuk, we have a couple of questions on the chat.
okay. So,
Um, okay. They're asking about inferior in terms of GDB terminology.
yeah.
Um, and then also what is lane?
So,
And they're asking about the thread lanes, I guess.
same deal, right, I guess. Um, yeah, so imperial is kind of terminology on GDB part, right? So imperial, maybe you are not familiar with this terminology, but it is kind of object to represent the state of the program execution, right? So you can think here. Uh, uh, so inferior one represent the debug state of the CPU state, and then inferior two is for debug the target debug mode, right? So I know I'm kind of yeah, it's kind of yeah. That's my yeah. Yeah, Harry should add some link, right? So I think you had better check in the link to see more details. So it's kind of hard to say definitions. You can think this is kind of object to debug a state, right? Represent the state of the debugging mode. So okay, it looks like Alfred is okay with that link. And then also download the thread has range. So on the Intel GPU, multiple devices running. So on the GPU, we have a multiple thread is running on the same GPU device, right? And then we also have the SIMD lane. So you can also, inside of the thread, you can also, depending on SIMD lane, you may have different data and different variables, different values, right? So because of that, we have thread and SIMD lanes. So maybe I can show some examples, showing example at the demo may be easier to understand what's going on over there. This is kind of the terminology. You may not familiar with this terminology, but once you see that, you may just understand what's going on over there. Okay, Simon put some additional comment. You can think of imperial as process, but the more general because GDB sometimes debugs when things aren't in process. For instance, you connect the stop and debug microcontroller and not the process. Yeah. Yeah, so Imperial 1 is usually process, but the Imperial 2 is inside of the process, you have the multiple devices, right? So that is what it's saying. So, yep, hopefully that makes you understand better. Maybe not perfect, but I hope so. Okay, let me move on to the DDT right here, right? So, you can download the client version and then you can configure remote client following the instructions. So if you click this link, we have GitHub repository here, so you can follow this instruction to how to set up your client version. So first of all, you need to start your client TDT client on your local machine, and you can see this kind of window popping up. Then you need to click the remote launch here. Now it's up, but if you click the remote launch, you can see the pull down. And then you can click the configure. So if you configure, you can see another window popping up here like this one. So I have already configured several machines, but you may want to add additional to Aurora. So you can just click the add here. So once you add, click the add, you can see additional window pops up. And you may just set the connection name, maybe set Aurora, and then host name. You can put I put my ID and then the login Aurora airset.n.gov You may just use aurora.asf.in.gov, right? And then this part is important. So remote installation directory. So you need to check where is DDT located after loading the module ports. And then you can just use that location for the installation directory. So again, once we have new SDK, we will have 25.0 version. Once we have that, you will have different locations. So you need to adjust depending on the location. So once you put that, you can just test remote launch, and then it will ask you the Aurora credential, login credential. If you type it, it will check the remote launch test is completed successfully or not, right? So that's how to set the instruction. Okay, Parachute says, does Linaro DDT has a finite number of license associate limit on the number of process it can debug? Yes, we on Aurora system, we have a pretty good volume of the Linaro DDT license. So it's per MPI rank base and also kind of combination of number of GPU support. So we have a pretty big license volume, and you can easily use the DDT license more than 20% or 30% of the system. So the one of the usage of the DDT is really convenient for debugging at scale. Sometimes, in theory, if you can run with multiple MPI rank, you should be able to run and the entire system. But then in reality, what happened was when you scale out at the sudden scale, we see some issue happen, right? So, for example, maybe if your MPIC layer have some defect at scale, and then you may just see some some rank number or some state number is kind of overflow, something like that. That kind of thing happen, right? So in that case, you can use Linux DDT, and then our system, I believe you can easily use more than 20% of the node with all the GPUs with our license. So you should be okay. And does anyone have experience using Linaro with containers such as Apptainer? That has been limitation of total view. So I haven't tested with container. That's good point. I will check it with our farm contact, and if it is available, we will extend our user guide for the how to use container. So for now, I have no idea exactly how it will work with container. In theory, it should work, but I haven't tested. Okay, so one of the strong point of DDT is DDT is available across the multiple architectures. So as you can see, it supports various compiler, Intel, Wacom, CCE, GCC, MBHPC, XL. And also it works with the various MPI settings. So Intel MPI, MPitch, OpenMPI, and it works with the Slum, it works with the Pulse, various OS, the Red Hat, SUSE, and Ubuntu. And you can, it also support different GPUs, AMD GPU, NVIDIA GPU, and Intel GPU, and also working with the different CPU architecture, x86 or ARM architecture. So once you use DDT on specific system, you can use the same instruction on the other system, and you can debug your code on other architecture. This is another strong point. Okay. And compared to GDB OneAPI, DDT provide a very nice user interface. As you can see here, this is an example. So once you start your debugging with DDT, you can see this kind of window popping up. At the top, you can see some process control. Instead of run, step, typing on the terminal, you can just click the icon and move forward, right? And then the bottom of the process control, you can see the process group. You can see what kind of MPI rank is working on, what is GPU threads in the lane is available you're using, right? And in the middle, you can see the source code. So you can see which line you make a breakpoint, and then where you are during your debugging process. On the right line, you have multiple tabs to see the local variable, current lines, and then current stacks. At the bottom, you can also evaluate some variables. You may just watch some specific variable or you may have some kind of formula with some local variables, see how those values are moving on. And the left bottom, you can see stack value or some watch point, break point in input and output. And left one, you can see the project file, and then you can also find the file and functions in this window. So compared to GDB1 API, GDB1 API provides very fundamental features and very strong debugger, but for the users, DDT provide better user interface for debugging application, especially at scale. So how to run the application with DDT on Aurora? So DDT is not part of one API, so you have to load additional modules. So you can do the module load forge, and then the forge will include the DDT. So how to run your application with DDT? First of all, you need to connect your client to your system. So connect your local Linaro client on your local system to Aurora from a remote launch pull down. So you configured on the previous tab, and then you just launch the, you just need to remote launch with Aurora. And once you establish your client version attached to your login node, you may start interactive job mode or batch mode, and then run the DDT-connect with your application. So for example, for the 12 API rank, I may just put the DDT-MP12 and then -connect. And I use MPI generic from the system, and the MPI argument is -ppn12 and the env all, just to pass over the environment variable and run my application here. So once you do that, what happens is your remote client, you will see another window popping up and showing some reverse connection request like this one. So, and then it shows a command line for the reverse connection. And then you can see, you can check which is your connection or not, right? And then you can just accept. And then you start this previous DDT UI for the debugging, right? So I will show you a demo. So this is kind of quick overview of GDB1 API and DDT, and I'm showing some examples. Before moving on, do you have any other question? Okay, if not, let me try that. Okay, so if you go to this GitHub repository, we have some quick example and some test file. Okay, so I just open up my the terminal for the Aurora. So I already on login node 12, and then I started the qsub-x for the X11 forwarding just to show the how X terminal is working on, and -l and select one and word time and file system and project and the queue, right? So once it start, you can see this compute node is available for my interactive jump mode, and then I will go to my example. So using the link, you can also download this example on your terminal. And then you can see these 5 different files. Excuse me, can you say again?
I think it's okay. I think maybe someone unmuted by mistake.
Okay, I see. Okay, so here, what you need to do is, first of all, you need to enable, uh, what is the, sorry, too many windows. Let me just close this one. Okay, so first of all, you need to establish the debugging configuration on the GPU, right? So in my example, I'm just using on a single MPI, a single node for the practice for the demo. So I will just do the MPI XAC-N1 and then helper toggle and put the 1. So once you do that, you can see EU debug state on rank 0, 1, 1, 1, 1, which means your 6 GPU device now debugging configuration is on, right? And then one additional step is you need to put the environment variable get enable program debugging is equal to 1. So you can just put it in here. So once you do that, now your compute node is ready for the debugging, right? So before moving on, let me just make my test example. So what I'm doing is using npicc. This is OpenMP uploading example. And I just build use -g -o0. Then I just created the compute geoseries and debug, right? So if I just run this example, it just get the simple geoseries computation and provide one. And I can also use -n12 GPU tile compact sh and then comp. I can also run this application with the 12 ampere length on different GPU types, right? So this is the example file, and then let me start GDB OneAPI -q, and then the comp and is debug. So once you start that, your GDB cursor is popping up, and then you need to set the breakpoint, right? So break, then let's set the breakpoint on comp geoseries omp.c and line number 32. Let's do that. And it says breakpoint 1 is set file comp geoseries omp.c line number 32, right? And then let's start to run. So if I run it, it just start thread, and then it is the showing the standard output. So it says GDB server-g start process 21:00:28, right? And then it just stop at the here. So uh, thread 2.2827 hit the breakpoint 1.2 with the sync lane 0 to 5, right? So this is the message you're seeing. And if I do the step, what happened is I may just check my info file here. So if you just list it, you can see what is info file looks like, and then your breakpoint sitting in the 32 here, right? So if I just step, you may expect you may move on your thread moving on the TMP, the second line. But what happened here is if you just step, instead of going the next line, it says, oh, thread 3.27 hit the breakpoint 1.3, right? So with lane this one. So actually, instead of moving on, another GPU thread is to hit the same breakpoint, and then you don't see the data anymore. So what I need to do is I may just want to look into what's going on with this specific thread. So locking step. So once I do that, I just hold all other thread, just pause, and then I'm looking into, I just move forward with this specific thread 3.227, right? And then if I do the step, now I'm moving on from ID line to the line number 33. And then I may just move forward, right? And then once on this line number 38, I may just want to see what is the variable TMP result here, and then you can see the variable, right? And then you may just set the backtrace. And this is very simple example, just only one layer, but in general, in application, you can see multiple core stacks, and you can see where you are. And also info imperials. If you do that, you can see in the slide, you only see the two lines. One is for the connection, the number 1, and for connection 1. Second is the number 2, connection 2. But in here, you can see 13 imperial happening here, right? And then the connection level is 1 and 2. So what happened is connection 1, process 200628 is native inferior to debug a host code, right? And then host side. And then this host side, even though I'm just using a single GPU without MPI, but all the GPUs are kind of visible from the GDB server. So GDB server just attach all the create all the inferiors for each GDB because GDB does not know which GPU will be used, right? So now, as a result, you can see 12 additional device inferior here, and you can see different PCIe address here, which means different GPU types, right? So yeah, this is going on, and it will be helpful to have a list of all debugging message for each debugging tool. Otherwise, we don't know how to interpret the message. Yeah, that's true. So you need some time to understand what's going on in the debugging message, right? So for GDB, that's true, but on DDT, with better user interface and user-friendly terminology is used, so you may feel better with that tool. Are there any known issue with GDB on API and certain checkpoint library, or have you never run into issue with checkpoint library in GPU debugging? Um, what do you mean checkpointing library? Checkpointing in from the application, or can you add more? Yeah. Mm, yeah, I haven't seen any issue yet. Um, because checkpointing library does not use GPU directly, right? This is kind of host side action. Is it right? If so, GDBs, we can debug host session as well. So you should be able to debug that application. But sometimes they may not resume properly because of checkpointing activity, you're saying? Yeah, I mean we need more specific case. Yeah, in theory, it should be okay, but in practice, no one knows, right? So if you have any specific issues with some specific library, checkpoint library, we can also work with Intel to resolve that issue. So just try it out with your application and let us know if you have an issue, okay? So yeah, so this is kind of GDB example. And then if you exit, all the inferior will be detached, and then you can back to the your terminal, right? So uh, if you're a really big fan of the GDB1 API, you may want to try MPI debugging with GDB1 API. So let me show you how to do that. So for that, you need to establish X11 forwarding from your local laptop to your Aurora login node, and then using qsub-x, you have to establish X11 forwarding from login to compute node. So once you do that, I will just use this example and here. So I will just use this example. So this example, I'm using npmd mode, and then I attach GDB1 API to the first MPI rank using xterm-e GDB1 API, and then do that. And then I'm running another remaining 11 MPI rank without GDB, right? So if you run that, what happened is I already established the XLM forwarding through the qsub-x, and then window, yeah, X11 window popping up on another monitor here. So now you just attach one GDB on API to the one MPI rank. You will see this tiny X11 window, and then you can set the breakpoint here and then run, etc. So this is usable, but the problem is attaching GDB on API on 100 node is not very easy and not it's not very it's very tedious process, right? And then yeah, a scale is pretty limited. You can do that, but pretty limited, right? So instead of that, we can try the Linaro DDT, right? So I will just load Forge. And if you check the Forge module, you have a 24.1.2 version as by the default. Again, once we update the SDK, we are going to have 25.0 version. So you can try that. And then now you have to start your local client version. So I just start my local client version here. Oh, let me start my local client version. So I already configured my local client version here. So Linaro DDT for 24.1.3 version. And then I already configured for the Aurora. So I will just click the Aurora. So I have some additional SSH config, so I don't need to type my login credential. But if you don't have that, you may be asked to enter your login credential. Now you can see on the right bottom, you can see Inaro port 24.1.3 config connected to the JQuack login Aurora ALCF.anl.gov, right? So you're here. So now your client is ready, and your interactive jam mode, you can start DDT, right? So let's go back to our example slide here. And then I will just run with the 12 MPI rank on single node as a demo. So for that, you can just do the DDT-MP12 and dash connect. This is required to establish reverse connection. And then MPI argument, PPN12, EMB all, and then compute geoseries, MPI CCDP debug, right? So once you type that on your compute node, you can also do the same thing on the batch mode here. And then if you go back to your client version, new window popping up here. A new reverse connection connect request is available. And this is command line I'm using here, right? And then if you just accept that, it is showing what is MPI application, number of MPI, open thread, and then Intel Xe. So you can just run it. And then it's just established 12 MPI rank, attached to GDB. I mean, DDT is using GDB under the hood. So basically, in terms of functionality, whatever available GDB, you can do on the DDT, right? So this window popping up here, right? On top, you can see control line here, maybe start and step and up and down. And you can also you can also see MPI rank here. So I would like to move forward by group by default, but you can also choose by process and thread, right? So once it starts, you can see on the source line, the very first line of your main function just stopped, right? And you may need to check the breakpoint here. So I said the breakpoint previously, so just remember that, but let's remove that here. So you may be interested in the line number 32, like we did on the GDB OneAPI, and then I will also set on the here breakpoint to all, right? So I will just set it here. So once I set that, what you need to do is you can just start, just click this icon here, then it start running. Then whenever one of your MPI rank, one of GPU thread hit the breakpoint, it will just ask, do you want to continue or pause, right? So yeah, okay. So while we are waiting, it will take some time, but let me see. So does Linaro DDT find what you are running on compute node automatically? Yes. So what I'm doing is on the compute node, I specify which application I'm running, right? So using the connect, right? So in this case, I want to use 12 MPI rank here. Then I want to use this application I want to run, right? So since I specified a DDT dash connect line, DDT understand which application I want to run. And then once you establish the reverse connection, you are just running that application. Okay, so now it says process 9 stop at breakpoint in the comp usage and then line number 32. Do you want to continue and pause? Let's try to pause here, right? Pause. So we are here. And if you check here, you can just see what is the variable in the command line, and what is local variable, and what is current stack, what is GPU device you're working on. And you can also evaluate window input, so you can see the standard output, standard input, and then breakpoint, watch point, stack, trace point, trace output, etc. Right? Um, so you can move forward, but you may be curious how is that the scheduler locking step, etc. Right? So here you can see the focus on the current. So you may just focus on current group, or maybe you just want to focus on a specific MPI process here, right? So you may just check it. That means you want to working on what's going on in this specific MPI rank 9, right? You just want to looking into that. Or But still you don't set the thread, so you can just set the thread, which means you just want to look into what's going on in this specific thread, MPI rank 9, and this is a specific thread, right? And then if you just moving on, you will just moving forward, and then once this MPI rank, this thread hit the next breakpoint, it will just stop. Okay. Yeah. So it's asking thread 9, and this thread is just hit the second breakpoint 38, right? And then you can pause, and then you can see the local variable. So this is kind of the different way. Instead of remembering all the GDB command, you can also just click and select some focus group, focus on current, and then you can move forward. So this is very nice, very simple uh, intro demo with the GDB OneAPI and DDT, and we have 12 minutes. Let me move on the next target. So another tool available on Aurora is Intel Sanitizer, which is a correctness tool to detect addressability issues, memory leaks, data race, deadlock, and use of uninitialized memory. So how it works is you need to build your application with Sanitizer additional compiler flag. So compilation build the sanitized device image based on the compiler device flag. I will show you how to do that. And then on the runtime checks for the existence of the sanitized image. If they exist, the runtime enables specify sanitizer layer in unified runtime module to support sanitizer functionality. So this is an example of the SQL code. So on SQL code, OpenMP code is the same. So you just compile with the additional compiler flag to enable the sanitizer. Then you will have the fat binary. And once you start this binary, submit device code and kernel running on device. And if error happen, it record error report. And that once the kernel finishes, it report to the host side. And then print the error message. Then you may abort and you may just continue to run, right? So this is kind of process. So you need to require, you have to compile your application with this additional sanitizer. So there are three types of sanitizer available on device on Aurora. So address sanitizer, we call it ASAN. ASAN can detect out-of-bound check, use after free error, misaligned access, mismatch LD allocation, misusing host device pointer, invalid kernel argument, mismatching queue. And I'm missing, but it also check the memory leak as well. This feature is available with the 24.2 OneAPI or newer version. So right now, 25.0 version is by the default. So you can use ASAN by the default OneAPI. Another feature is a memory sanitizer called MSAN. MSAN can detect the use of uninitialized memory. And this feature is available 25.0 version, so you can use that on the default module on Aurora. The last one is the TSAN, thread sanitizer, to detect the data log and the data race condition. And this feature is available in 25.3 version, so we don't have that version, but we have some engineering draft to test our application. It works pretty well with our application. So once we have 25.3 OneAPI version, you will be able to use TSAN. So how to do that? So with ASAN, I just use a blue color, shows additional compiler flag and additional runtime environment to enable the ASAN feature. So in order to enable device-side ASAN on SQL kernel, you need to add these two additional flags, X arch device and F sanitizer is equal to address, and build your application. And once you build the application, just run it with one API device selector level 0 colon GPU. Then ASAN will start running. On OpenMP side, compilation flags are same, XR device, Fcent address, but the runtime environment is slightly different. The reason is SQL side, we are using unified runtime as by the default runtime. But OpenMP, we have unified runtime is not the default runtime. So we have to use libomptarget target plugin unified runtime. And inside the unified runtime, we have to enable the UR layer ASAN. So you need to add these two runtime variable and then run your application, and ASAN will running with your application. So this is example message from OpenMP portion example. So at the beginning, your application standard output will say device sanitizer ASAN is enabled here, right? Then whenever the error captured, it shows error, device sanitizer, out of bound access on device USM. And then it will show you which line, which file, which line got the error. So you can go to, this is a games example tested on Aurora. You can go to the TGPU OMP mode SP F90 and then 106. This is kind of embedded error. So games developer don't need to worry about that. But anyway, this is kind of example of the code. And this is some secret example, simple benchmark example. So what happened here is we just malloc device with 1024, and then in the pattern 4, what we try to increase the values with the wrong index plus 1, right? So we just touch outside of the array. So in this example, it says device sanitizer out of bound access happen USM, and then showing the file and the line number. OpenMP side, Fortune OpenMP side, again, we just allocate length, array A with length, and then we just run the do loop with the length plus 1. So we just hit the out of the bound. So you can see the out of bound access on USM, and it shows the line number and then file name. So you can check it. For the memory sanitizer, it's very, very similar to what happened with ASAN, but the only difference is you just put the F sanitizer is equal to memory on the SQL and OpenMP code. And UR enable layers, instead of UR layer ASAN, you need to select UR layer MSAN for OpenMP code, right? And then you can see at the beginning, device sanitizer MSAN is enabled, and then whenever it hit the error, it will show the warning use of uninitialized values, and then show the file name here and line number. This is some kind of the MSAN examples. Again, the SQL example we have, we just allocated here SQL accessor ACC, and then we never initialize that. And then here we try to use ACC array with the check function. So Sanitize said, oh, you had better know you are trying to use this array without reinitialization. So in this example, you can see the warning device sanitizer use of an uninitialized value, and then you need to check local accessor, the CPP, and the number 15. So this is some kind of a example with which application? Yeah, some application, I think. And then this is fortunate example. Again, we just allocate A, and then we never initialize that, and then we try to use A value in the inside of the input statement, and then it's saying, oh, we need to. This is warning. So device sanitizer says detected a use of uninitialized value, so you need to check it, and then you need to check this file and line number 18, right? So last part is the thread sanitizer. This is to check the deadlock and database condition. Again, similar to MSAN, you just need to change F sanitizer is equal to thread instead of addressor and memory. And with OpenMP case, you need to enable layers, UR layers for the TSAN instead of MSAN and ASAN, right? So instruction is pretty similar. This is example. So once you enable TSAN, you will see at the beginning of the stand output, you will see the device sanitizer TSAN enabled. And then whenever error happens, you can see device sanitizer detect database condition, and you need to check this file, line number 10. So here, what happened is we just allocate an array with size of 1, and all the pattern for thread try to increase this array for the same index. This is a race condition, right? So if it happens, you can see that array is detected, and then the file name, and then line number. This is an OpenMP case here. Again, we have A array allocated, and then A array, instead of using different index, all the pattern OpenMP thread try to update A0, which is the definitely the data race condition. So the TSAN keep warning about the data race when write the size of 8, and then you can see the file name and then number. So this is all the reference I use. So in spring, we had the hackathon, and yeah, Sergey Sleeve gave us a very nice detailed talk about the Intel GDB. So we have the record bad videos. You can check that. And Rudy Stan from Linaro gave us another nice talk for the how to use DDT on Aurora. So you can see the slide deck, and you can also see the record here. And if you want to go more details about Intel GDB user guide, you can go to Intel GDB documentation. Sanitizer. Intel also have a very nice showcase about how to use Sanitizer. And Linaro DDT has its own user guide supporting all different devices here. And we also have our own user guide for debuggers here. And you can see how to set up GDB on our system, how to use DDT, start our DDT, our system. And also, you can, if you go to this GitHub repository, you can also grab the example I tested on Aurora. So you can also test it out on Aurora if you have any allocation. So this is all I have. Thank you for attending my talk. Let me check the chat here. So, does any of debugging tool work with Julia? Um, I don't. I haven't tested Julia because Julia is not a major supported language on our platform. Um, so I'm not sure about that. Definitely debugging tool support Python because Python is one of the key component for the machine learning framework, but I'm not sure about Julia. How much overhead do these sanitizer add? Should this not be used on production bit? Yes. Sanitizer team tested some overhead study with our application side. It depends on the application, right? Because ASAN, MSAN, TSAN has different architecture to detect errors, so they have different cases. And also, uh, we don't see any depend overhead characteristic per compiler type, but depending on application workload, if you have so many small memory access, sanitizer overhead can be very heavy, and it depends on the memory access pattern, right? But in general, we see more than 10x slowdown, sometimes 30x, 50x slowdown, depending on the application. So our recommendation is, if possible, try to reduce your workload size and your runtime as short as possible, and then try to use the sanitizer to detect the issue. So yeah, definitely it's not recommended in the production build. Yes. Okay. So any other question? Yeah. Again, so those tools are available. So try it out, and with your application, again, in theory they should work. But while we're developing Aurora, whenever we try some application, we could easily find out some unexpected bug, right? So we have a pretty close collaboration with Intel and Linaro for the debugger and sanitizer and DBT. So just try it out, and if you have any issue, feel free to reach out to me or ALCF support desk, so we can help you out.